Okay, today we are going to finish up our review unit packet. So we're on page 26, talking about key features on the graphs of exponential functions. So the stuff we're going to see today, we have seen before with our linear functions and with our quadratic functions. So I'm going to ask you questions like, what's the y-intercept and what does it mean in the context of the problem? Or f of 4 equals what? And interpret that point for me. Okay, so that's the type of stuff we're going to talk about for today. This time, again, with exponential functions instead of linear or quadratic. So let's start with number one. Again, we're on page 26. For number one, our graph shows us the amount of caffeine in a person's body after they have consumed a cup of coffee. So my first question, what's the y-intercept and what does it mean in the context of the problem? What's our y-intercept here? Yeah, we're looking for where does our graph cross the y-axis. Our scale is by tens. If we look, this is 50, so 10, 20, 30, 40, 50. So this would be 120. So our y-intercept is 120. And now what does that mean? 120 what? 120 milligrams of caffeine. Right when I drink my cup of coffee, right? Remember, anytime you are interpreting a point for me, I need to know both the x and the y values at that time with their labels. So I would say there are 120 milligrams of caffeine in the bloodstream right after drinking the cup of coffee. I could also say that this would mean that the cup of coffee had 120 milligrams of caffeine. If I drink the cup and then I have 120 milligrams, that must mean there would have been 120 milligrams in the coffee, barring any other extenuating circumstances. B says find f of 20 and interpret it in the context of the problem. Function notation here. So f of 20 means my x value is 20. So I'm going to go to where my x value is 20 and then follow that to the point on my graph. What I want to report out then is the y value that matches. I know the x, so what's the y? The y would be 10. So f of 20 equals 10. Now, what does this mean in the context of my problem? F of 20 equals 10. What can I say here? Yeah, exactly right. After 20 hours, there are 10 milligrams of caffeine in the bloodstream. That's what's left after 20 hours. And then C is asking us, does this relationship between time and caffeine represent exponential growth or exponential decay? What are we seeing here? Decay, right? The amount of caffeine that we have is decreasing. So this would be exponential decay. Good. Questions for me on number one? Okay, let's take a look at number two. Our graph now shows us the number of bacteria in a petri dish over a period of time. Does the relationship between time and number of bacteria represent exponential growth or exponential decay? This one's growth. Our number of bacteria is increasing over time. So this is exponential growth. Part B, find and interpret f of x equals 4. So this time I don't know the x. That's what I'm trying to find. I know my y value is 4. So I'm going to go to where y is 4, follow that to the point on my graph, and then see what the x value is. So our x value here would be 2. F of 2 equals 4. What does that mean in the context of our problem? F of 2 equals 4. Throw those labels in there for me. After 2 minutes, there are 4 bacteria. After 2 minutes, there are 4 bacteria in the dish. For C, we're going to write a function that represents this. We actually did this the other day. So when we started our section on exponential functions, the very first thing we did was graph exponential functions. And after we had graphed a few, then I gave you a graph and asked you to write the function from the graph. So we're going to do that here. Now, the thing that we're missing is our asymptote. But if I look at where the graph tapers, it appears to be right about here. So I'm going to say that my asymptote is 0. So as I write my function, I can put that plus 0 at the end. Since it's 0, I actually don't need to write that, but it's not wrong if I do. And then I'm going to look at my point on the y-intercept, or on the y-axis, I should say, which would be my y-intercept. So this point right here, its distance from the asymptote is 1. So that means my lead coefficient, my initial value is 1. And then for my base for the exponent, I want to look at how that distance changes. So as I move forward a spot, now my distance from the asymptote is 2. So 1 times what gives me 2? 2. So the base for my exponent is 2. Just like we did the other day. I've got one more question for you about problem number 2 here, and it's from our function. So the base for the exponent in our function, that base we said is 2. What does that mean in the context of our problem? Our bacteria in the dish, what's happening with them? It's exponential growth. And that also tells me how much it's growing by. So we're growing by a factor of 2 here, or we're doubling the number of bacteria in the dish every minute. The number of bacteria doubles every minute. Questions for me on number 2? Okay, I want you now to try 3 and 4. We've done a bunch of these types of problems together. I want you now to try 3 and 4. So tell me about the y-intercept, interpret some function notation there for me. 3 and 4. Okay, let's take a look at these. Number 3, find and interpret the y-intercept. What's our y-intercept here? 400. And then the context of this problem is that we're looking at medication in a bloodstream after you've taken it, sort of like our caffeine problem. So if I am interpreting this point, what would that mean? Yeah, perfect. Right after taking a dose, you have 400 milligrams of medication in your bloodstream. If you told me something like what we said with the cup of coffee problem, that a dose of this medication is 400 milligrams, that would work too. How about F of 2? What is F of 2? $200. Yeah, I go to where my X value is 2, follow that to the graph, and I'm looking for the Y. F of 2 is 200. So this would mean what? Perfect. After 2 hours, there are 200 milligrams of medication in your bloodstream. Perfect. And then C says, it's safe to take a second dose when the level in the bloodstream is below 50 milligrams. When will the person be able to take their next dose of medication? How long do they have to wait?
They can take their second dose of medication
after 6 hours. So I'm going to look for when I thought, if I look at my scale here, here's 200. So this would have to be 100. That makes this 50. I'm looking at when do I hit 50 milligrams? That would be at 6 hours. So after 6 hours, you're good to take a second dose. After 6 hours. Questions for me on number 3? Okay. And then number 4, we're looking at a pot of boiling water after the stove has been turned off. So we had water boiling on the stove, we shut the stove off, and then we looked at what happened. Before we even look at the graph, what do you expect to happen? The temperature is going to go down, right? It's not going to just keep boiling independently. It needs a heat source to do that. So let's find and interpret the y-intercept of the graph. Now, let's think a little bit about back to what we've learned in some of our science classes. If the water was boiling here, what temperature would I expect that to be? Based on our graph, we have to estimate a little bit, but we should know the boiling temperature of water. Oh boy, I'm going to email your 5th grade teachers and they are going to be mad at you. It's 100 degrees Celsius. We're in Fahrenheit. Not quite. 212. 212. Okay, 212 degrees Fahrenheit. So my y-intercept is 212. Again, based on the graph, we would need to estimate. So if you didn't know anything about the temperature of boiling water and you estimated 210, you'd be close. We should know that it's 212. So as I'm looking at what this point means, that means the water was 212 degrees Fahrenheit when we turned off the stove. And now we've got some more function notation here. F of 7. What's F of 7? Yeah, I'm going to go to where I've got 7 on the X and follow that to the graph. If this is 100, our scale would have to be like 20, 20, 40, 60, 80. So F of 7 is 80 here. So what would this mean in the context of our problem? After 7 minutes. After 7 minutes, the water is 80 degrees Fahrenheit. And now, before we get to C, I want you to think for just a second about what happens as this water is cooling. We said it's going to keep cooling down. Is it going to keep cooling indefinitely? Like eventually I'll look and it's just a pot of ice on the stove? No, right? What's it going to cool to? Room temperature, right? It's going to balance out with whatever the ambient temperature of my room is. So for an exponential function, what we're looking for there is going to be our asymptote, right? The water shouldn't ever be colder than room temperature. If it's boiling and it cools down until it reaches some sort of like stasis, that's going to be room temperature. So again, we don't have our asymptote graphed on here, but let's say, just for the sake of ease, that this grid line right here is a good approximation for our asymptote. Maybe it's up a little higher. Let's just use that grid line as an estimate, as an approximate. So this would be at 60. So our water is going to cool, continuing to approach room temperature, right? So what would we expect room temperature to be for this kitchen? About 60 degrees. Degrees Fahrenheit. Questions for me? Okay. Again, same stuff we did with quadratic, same stuff we did with linear. If I have a graph and a context, we can interpret information based on what we know our X and our Y represent. So that is it for our review for our exponential functions.